General characteristics of transition elements. First one is they have typical metallic structure except mercury, which is a liquid. For example, ZnS. It has BCC type of structure, bodied body centered cubic structure. Similarly, other elements of D block, they form typical metallic structure. Next property, their atomic radii are in between those of S block and P block elements. S block elements has the uh, larger atomic radii. P block, when we move from left to right, atomic radii decreases due to increase in effective nuclear charge. And the D blocks have atomic radii in between those of S and P block elements. Next is they have high melting point, boiling point, high enthalpies of vaporization, high enthalpies of atomization, and high enthalpies of hydration of their ions. High melting and boiling point of transition elements is due to the strong metallic bonding. Strong metallic bonding because they have low ionization energy. As ionization energy decreases, they easily form metallic bonds, and the metallic bonds are stronger than the uh, van der Waals forces of attraction. That's why they have high melting and boiling point. They have also high enthalpies of vaporization. They require more energy to change from one state to other. For example, like from liquid to vapor state because of strong bonding. Next is they have high enthalpies of atomization, means energy required to change the metal into metal atom. And high enthalpies of hydration means hydration enthalpy. Hydration word represents the water molecules, means when water molecules approach towards the cation, they require some energy, and this energy is called enthalpies of hydration, and for transition element it is also high. And next is first ionization enthalpies of transition elements are higher than those of S block and P and lower than those of P block elements. As we already know that and ionization enthalpies increases when we move from left to right in a periodic table. This is due to the increase in effective nuclear charge with atomic number. And next is the electropositive in nature. All the transition elements are electropositive in nature, means they have tendency to lose electrons. Next, they show variable oxidation state. This is due to availability of vacant orbitals. They show variable oxidation states in which ns and n-1d orbitals are involved. Next is the stability of any oxidation state depends upon its electrode potential. Electrode potential, it is the potential difference between electrolyte and its ions. And the stability of any oxidation state depends upon the electrode potential. More negative is the electrode potential, more easily it get oxidized. Next is they show catalytic properties. Most of the transition elements are used as a catalyst in many chemical reactions. For example, vanadium pentoxide is used as a catalyst in in the preparation of manufacturing of chemicals. Similarly, platinum, iron, nickel, these are used as a catalyst in the organic reactions because they have free valencies on their surfaces and the reactants get adsorbed on their surface, and when they detached from the surface they form products and catalyst is regenerated. Next is they form colored compounds. This is due to the presence of unpaired electrons in d block elements. Next is paramagnetic in nature. This is also due to the presence of unpaired electrons. Greater the number of unpaired electrons, greater is the paramagnetism. Transition elements also form complexes, interstitial compounds, and alloys. Interstitial compounds, for example, Fe3H is the interstitial compound. This is Fe3H, in which iron crystals have some vacancies or voids in which this hydrogen atom is fitted in the interstitial sites and forming a interstitial compound. And transition elements also form alloys like brass, bronze, etc. Trends in properties of transition elements. Atomic and ionic radii. Atomic and ionic radii, they regularly decreases in the series at the midway, like this. After the midway, the decrease is small. There is small decrease after the midway, and in case of zinc, cadmium, mercury, there is slight increase. When we move from, in case of first transition series, scandium to the midway, means manganese or iron, there is a decrease of atomic radii. This is due to the increase in effective nuclear charge. As the atomic number increases, effective nuclear charge also increases, and hence the atomic radii decreases. But when the number of electrons increases, like in case of from manganese to iron to cobalt, there is a poor shielding effect of d orbital exist in this case. Poor shielding effect of d orbitals. They do not properly shield the outermost electrons from the nuclear attraction, and hence the nucleus holds the outermost electrons more tightly. That's why their atomic radius decreases after the midway, but the decrease is small. But at the end of the series, in case of zinc, cadmium, and mercury, there is a slight increase of atomic radii. This is due to the electron repulsion. The electron cloud expands and hence the atomic radius increases in case of zinc, cadmium, and mercury due to fully filled d orbital. In case of zinc, cadmium and mercury, they have fully filled configuration. Due to electron repulsion, their electron cloud expands. That's why their atomic radii or ionic radii increases. And in case of second and third transition series, as you can see here, they have almost same atomic radii and ionic radii. This is due to the lanthanide contraction or the poor shielding effect of d and f electrons, and the lanthanide contraction. Next is the ionic radii. In case of ionic radii, in having the +3 oxidation state for first transition series, here it is first transition series, scandium to nickel. As the number of d electrons increases from scandium to nickel or cobalt, there is a decrease in ionic radii. This is also due to the increase in effective nuclear charge. As the effective nuclear charge increases, atomic and ionic radii decreases. And this another line represents the other oxidation state of the elements. Melting point and boiling point of the transition elements. Melting point first increases, rise to the maximum, and then decreases in three series: 3D series, 4D series and 5D series. Here in case of first transition series from titanium to chromium, it first increases to its maximum and then there is a dip in case of manganese and then again decreases. Here it is lowest, manganese has the lowest melting point and boiling point. Similarly, in case of second transition series, technetium is the lowest melting point and boiling point. And in the third transition series, it goes to tungsten, which is maximum, and then again decreases from tungsten to the mercury. The reason behind this is the number of electrons increases. When the atomic number increases, the number of electrons also increases. As in case of chromium, its electronic configuration is 3d5 4s1, which is exactly half-filled configuration, and it forms the strong bond. Due to exactly half-filled configuration, it forms the strong bond and its melting point is higher. But in case of manganese, it also has 3d5 and 4s2 electrons. Due to this exactly half-filled configuration in this, manganese have a tight hold over these electrons and they are not they are less delocalized and they form weak metallic bond. That's why their melting point is lowest in its series. And when in case of iron, again the electrons 3d6 4s2, number of unpaired electrons decreases and hence the melting point is shows the slight increase. Similarly for the second and the third transition series. and this depends upon the enthalpies of atomization. As the enthalpy of atomization increases, the melting point also increases. It means melting point depends upon the metallic bonding. When the bond is strong, it requires more energy to break, and the melting point of the element is higher. Metallic character and densities. All the transition elements are typical metals due to their low ionization enthalpies, means they have tendency to lose electrons and form metallic bonds. In metallic bonds, both Ns and N-1 d electrons participate. Greater the number of unpaired electrons, stronger are the metallic bond. As in case of chromium, it has greater strong metallic bonding due to 5 unpaired electrons in 3d orbital and 1 unpaired electron in 4s orbital. As the number of unpaired electrons decreases, metallic bond strength also decreases and the metallic character also decreases. Next is the densities. Densities increase along a series because atomic size decreases. As the atomic size decreases, volume increases, whereas the atomic mass increases. Because densities depends upon atomic mass. When the atomic mass increases, density of the element also increases.